So now I'm going to start to talk about the impedances. Up to this point, all we talked about was the basics that we need to start to work with the ACs. So the complex number, the phasors, the sinusoidal signal. And from this point, start to actually look at how we can start to work with the impedance. Uh, Slowly, as I go ahead, I will say what is the impedances and how we use them. But as a very quick note is like that when we have the resistance, um, we would say that V is the um, basically V is the resistance time the I. So we would write that for the resistance in the DC form, we would say that V is the R times I. If we have in DC system, this is what we have. V was the RI. Now, when we come to the AC format, we want to keep this format as well. So instead of writing in that in the AC format, we will write it as V is gonna be, instead of R, we write it as a uh, I would say Z, and then I would write it as a I. So V and I are um, time dependent AC voltage and current. This Z here is gonna be called impedances. So basically, it's the same Ohm law that we have it here. Here in the DC format, we have it as a V is R times I. Here we call it, instead of R, we call it Z. And so it's the V equals Z times I. So V and I are time dependent, and the Z is equivalence of is sometimes like something, if you want to conceptual look at it, something similar that we have as a R in the DC. So we are going to have it as a Z here as a impedances. So the impedance, that's Z, uh, it's going to be, usually it's going to be, the Z is going to be in the complex format of R plus J X. Some is usually written like that. I will go through that. What are these slowly. The R is the resistance. So if we in the is the resistance. If we have the resistance in the system, is going to be R, as we have in the DC. So R is always um, real part of that impedance. So if we have the resistance form the real part of that impedance. And this is um, what I call it, that is going to be reactance. And this X part is as a function of inductor or capacitor. So for now, just look at it at the way it is, and slowly I will go through them, what actually each of them means. So one more time, we have a simple Ohm law in the DC. So we want to have the very similar one in the AC format. So we write it V is equal to Z times I. Z is the impedance, and the impedance here, R is the resistance of the DC. Here impedance is made of the resistance, the effect of the resistance, and the effect of the capacitance and inductance. So when we put them together, so we put the resistance plus the effect of inductance and capacitance together, is going to form a complex number, which is called the impedance, and then we put it there. And slowly I will go through how we can actually calculate that and use it in this equation. So the very first one I want to talk about it is the uh, impedance for the inductance. So if I impedance for inductor, assume I have a single inductor in the system. So what's the impedance for that? How it's going to be? So if I have a simple inductor in a system, what I have assumed my current is going to be I max, and then sine omega t plus theta. Assume this is the current equation I have, and I can write it as we know before. So I can write it as I max as cosine omega t plus theta minus 90. And then I can write it as impedance. So if I said, let me put the L here so I know it's for the inductance. So I can write it as the I would write it as a phasor. So it's going to be the IL, the current in the impedance is going to be the I max, and then with the angle of theta minus 90. So this is what we are going to have as a current. So if this is a current in the inductance, this is a phasor of the current in the inductance. Now let's look at what's the voltage. So if I have that, I know that the voltage of inductor is going to be the L dit over T over dt. So we know that this is the voltage of the. So if I take the derivative of this term here, is gonna become so it's gonna be the omega L I max cosine omega t plus theta. So if I take a derivative of this term and times it by L, this is what I'm gonna get, and therefore I can write it as form of again a phasor. So it's gonna be the VL is gonna be omega L I max with angle of theta. So these two equations we have. So I have the IL and VL as the format of the phasor. Now remember the equation I wanted to write. I wanted to have the equation as this: V is equal to ZI. So I'm gonna find out how I can write a V is equal to ZI here. So if I go here and say that, okay, the VL here is equal to omega L I max with angle of theta. So I can go ahead and write that and break it into two parts. So I can write it as a omega L with angle of 90 times I max with angle of theta minus 90. So look at where these two terms come from. So if I come here and write this in format of the exponential format, you might see better. So I can write this as a omega L e to the power of j 90, and I can write this as a I max e to the power of j theta minus 90. Now look at that. If I multiply these two, this one is, if I write this, is going to be omega L I max e to the power of j theta. So if I multiply these two, it's going to give me this. These two, if you multiply these two, it's going to give me this. So it's, if you wonder where these two terms came from, it's like this. I just write it in the exponential format, then break it in these two terms. So that 90 will cancel out with that 90 and only theta remain there. Now look at what I have here. This part I max theta 90 is just the IL. So this is the IL. So if this is the IL, I can write it as VL is equal to omega L with angle of 90 IL. Now let's go back and look at the impedance here, this equation. This is what we are looking at. V is equal to Z times I. This is what we wanted to find out. V is equal to Z times I. And look at here, we have the VL is time this term is equal this term times I. So this term is the ZL. Because look at that here, is the V is equal to ZI. So we have V and we have I. So this term here, it should be Z. So this is going to be the Z L that we have. So in other words, I can come here and write it for, if I have on the inductor in the system, I can write the VL is similar to the Ohm loss, is the ZL times IL. So this is the equation I have. It's similar to the Ohm law, but for the phasor format in the AC domain. And then ZL is omega L with angle of 90, which, if you know that the omega L with angle of 90 is just simply J omega L. Because when we have the angle of 90 means that we are completely on the imaginary axis. So everything is going to be on the imaginary axis. So it's going to be just simply IL there. And so this is also the impedance for the inductor. So if I have only inductor, the voltage, and I have only inductor in the AC current, the voltage and the current are related together through that impedance, and the magnitude of that impedance is just J omega L in the calculation. Now if I go ahead and draw the V and M, so let me just so I again I know that the I here, I'm going to just write these two equations, these two, the IL was the I max sorry, the I max with the angle of theta minus 90, and the VL was omega I would say the omega L I max with angle of theta. So these two equations here, these two. Now, if I just simply go ahead and assume this is the Vmax, not assume, this is actually a Vmax. So I can write it as V max with angle of theta. Now, if I go ahead and draw these two, together, so first I draw the Imax, IL, so you can do the Imax with theta minus 90 degrees, or let's draw this one first. So assume it's the Vmax with theta. So assume this is gonna be it's gonna be the VL, which is the Vmax with angle of theta. So this angle is gonna be theta, and the length is just Vmax. Now, if I want to draw this IL is the Imax with theta minus 90. So if it is theta, I have go ahead minus 90 degrees. So it's gonna come something like this. Oh, let me draw it a little. So if I have this one, so it's gonna be IL, which is Imax with theta minus 90. So if this is a theta, I know, so this is going to be the right angle here, because there's a 90 degrees between these two. So that's the theta minus 90 degrees. So we go theta minus 90 degrees here. So there, if you draw them, they're going to look like this. So it's a theta here. Then if we go from here 90 degrees back, we will get to this one. If you look at here, it basically, what it tells us is that in pure conductance, if we have only an inductor in the system, for pure inductor, if only we have inductor in the system, what we will say that is that the current, look at here, current lags voltage by 90 degrees, or voltage lead current by 90 degrees. So the voltage leads current, or the current lags voltage by 90 degrees. And what what actually it means that if let me try if I can draw them, is that if I draw if I have a time, and if I draw, for example, the current and for example, and the voltage. So if I have the, assume I have the current going like this, if this is the current, if this is the current, then current lags voltage, or the voltage leads by 90 degrees. So So let me draw them with the same color. So I draw the current here blue. So let me draw it with the blue here. So if I have, this is the, so if I have, this is the current, then the voltage in a time domain, if this here, the voltage would be somewhere here. So for example, this is going to be so this is going to be the voltage, something like that. So let me make the amplitude difference. So for example, this is going to be the voltage, something like that. It goes up to here, goes down, for example, to here, then goes up to here, then goes back down here, or something like that. So, and then you will see that between these two peaks, this is 90 degrees. This is 90 degrees. If I come here and change these to, instead of t, change it to omega t. So you see that the the voltage leads. So look at it. If I have the peak here, then the current peak happened after 90 degrees. So if that's why I say the voltage leads or the current lags. So whenever the voltage happen, the current happen 90 degrees. Whatever happened in the voltage, the same thing, the same trend happened in the current with 90 degrees later. So we can see it in the peak. So the voltage reached the peaks and the current reached the peaks 90 degrees later. So they are not on top of each other. There is some lag between when the voltage reach to the peak or reach to the minimum value here, and 90 degrees later the current does the same thing. So next, we're looking at for the impedance for the capacitor. So the impedance for capacitor. So again, as I said before, the whole idea is that we'll go back is here. If we have the something similar to Ohm law in the DC, we want to have something similar to that in the for the AC current. And then if we see that if we have the impedance, if we have only inductor in the system, it's going to be look like this. And if we do go through the calculation, this is we will get the same things for the capacitor as well. So we can write for the capacitor, we can write it that the voltage in the capacitor is equal to the impedance for the capacitor times current in the capacitor, and then the impedance in the capacitor is equal to negative j 1 over omega c, or basically is 1 over omega c with angle of negative 90 degrees. So this is what we have for the capacitor. So similar to the inductor, if I assume that the V in the inductor, sorry, in the capacitor is gonna be V max with angle of theta, then so if I assume this, then I know, look at this equation, the capacitor is going to be the VC divided by ZC. So if I do that, so the VC, if I assume, is going to be the V max with angle of theta here, divided by ZC, which is going to be negative J 1 over omega C. So if you go ahead and do the calculation, we are going to get the omega C, the omega C V max, and then it's going to be, or let me one more step, I write it so you can. Here, instead of writing like that, let's write it like this. So instead of writing a negative J, let's write it like, so the ZC, let's write it as 1 over omega C with angle of negative 90. So we know that we just divide the magnitude and subtract the angle. So the magnitude is going to be omega C V max, if I divide these two, and the angle is going to be theta minus theta, which is going to be plus 90. So basically, we subtract this from this, is going to theta minus negative 90, which is going to plus 90. So, and again, if I consider this as an I max, which is, then I can write this as a I max with the angle of theta plus 90. So if I go ahead and draw these two, draw this one, the V, and the VC and IC, I can come here and so if I come here and draw the, so for the VC, again, I have V max with angle of theta. So assume this is the VC, which is the V max with angle of theta, and basically this is going to be theta. And then I have I max with theta plus 90. So whatever is the theta, I have to add 90 degrees to that to get to the I. So if I add 90 degrees to that angle, I will get to the I, and assume this is going to be the IC, which is going to be the I max with angle of theta plus 90. So this angle between them is the 90 degrees. So similar to inductor, so for pure capacitor, well, look at here, the voltage lags the current, or the current leads the voltage. So look, I can say the current leads voltage by 90 degrees, or voltage lags current by 90 degrees. So if I look at this, so again, we consider everything counterclockwise. So counterclockwise, I is ahead of V, so we say that is leading that. So again, I'm trying to show you what does it mean. Again, is that when we say the current leads, this is omega t, When we say the current leads, it means that whatever happened in the current 90 degrees later happened for the voltage. So if I go ahead and assume that I have the voltage is going like this. So if this is the current. So if this is the current going like this, whatever happened to the current, 90 degrees later happened to the voltage. So basically it goes, for example, it goes from like that. And then if you, for example, again, look at these two peaks here, it is 90 degrees. So it means that whenever that, oh, sorry, you consider these two peaks here, 90 degrees. So it means that whatever happened for the current, it happened for the voltage by 90 degrees lag. So the voltage lags 90 degrees behind. So it reached a peak here, and the current reached a peak 90 degrees later. Next one that I want to look at it is if you look at the impedance for resistor. If you have only have the resistance in the system, what would happen? Again, if I go back to the here, look at what we have here. As I said, we have the something like that, and we want in the DC, the Ohm law, and want to have similar something similar to that in the AC. So it's going to be VZI. Now, if you have the AC current and only the resistor, we want to see what's happening to that, what's going to be that equation. And in case of resistance, is going to be the most easier. So it's going to be the VR is going to be just R IR, which the R is just simply the resistance. So the it's just the resistance. So basically the Z for R is just R. If this is the ZR, the ZR, so impedance for the R is just the magnitude of the R, and it's going to be in the real format. And as you can see here, whatever is going to be the voltage, because R is just a simple magnitude, it doesn't have any angle in that, the I is going to have the same angle. So whatever is going to be VR, whatever is going to be the angle of VR, the angle of IR is going to be also the same things here. So for the resistance, what we are going to have is that if I draw them, if we draw the V and I, it's going to be that so if I draw the V, and this is going to be the V, so it's going to be the VR with angle of theta, then the I is going to have the same angle as well, just different magnitudes. So it's going to be, this is going to be the IR with the same angle of theta. So both of them have the same angle. So for pure resistance, in AC current, what we can say is that the current and voltage are in phase. Are in phase means neither of I or R leads or lag the other one. So if I go ahead and draw them, so it's going to be omega t, and draw the V and I. So if I, for example, draw the I. So if I draw the I and the I goes like this, then we'll and draw the V. The V is going to be again we're the same as case of the peak and the trough as the, so you see the peak happened at the same time, the zero happened at the same time. If for example this one is going to be the IT, and the next one is going to be the, this one is going to be the VT. So we see the VT and IT happen at exactly whenever they reach the peak, they reach the peak together. When there are zero, both are zero. When they reach the minimum, they reach the minimum together. So they would say that they are both in phase. Next thing I want to talk about them is the impedance in series and parallel. So in series, series and parallel. So when we want to, if we have the impedance in series and parallel, in other words, if we have a couple of if you have resistance, inductor, and capacitor all in a circuit, and respect to each other, they can be considered as a series and parallel. What we do is that we write all we write the impedance for the resistance, for the capacitor, and for the inductor. And when we write them, we just treat them the way that we treat the series and parallel resistance. Any way that, so if the resistance was in series, we add all the resistance together, similar to here. If the impedance are in series, we add them together. And similar the way that we calculate the resistance if they were in parallel, we calculate the equivalent impedance the same way as we did for the resistance. So I'm gonna show you through the example how we do that. So assume we have a circuit like that it goes, and there's a capacitor with 12.5 microfarad. And then it connected to resistance like this with 200 ohm. And then here also I have one resistance, here 100 ohm. And then have the inductor with 0.1 Henry. And then we want to find the equivalent impedance for this. So finding equivalent impedance is like to finding the equivalent resistance. And when we were working with some resistance. So the very first thing to do that when we want to find the equivalent impedance is that we go ahead and write the impedance for all the elements we have in the system. So if I go ahead and write the impedance for all the elements in the system. So the very first top one that I have. So the very first one I have is this capacitor. So we note for the capacitor, the for example, the ZC for the capacitor, impedance for the capacitor is the negative J divided by omega C. So this is what I have. Assume the omega. The omega is given as 1000 radian per second. So we know the omega. So I can go ahead and say, okay, so it's going to be negative J divided by 1000, which is going omega, and then times 12.5 times 10 to the negative 6. Here, or let me write it down here, it's probably easier. So if I come here and say the ZC that I have is going to be negative J divided by omega C. So it's going to be negative J divided by 1000, then times 12.5 times 10 to the negative 6. And then if we do the calculation, it's going to become negative J 80. So I will come here and write the final value, save the space. So it's going to become negative J 80. So for that top capacitor that I have. Then I go next to this one. So I know that the ZR, so the ZR is just the R. We know that for the resistance, the impedance for the resistance is just the R. So for this one, the Z is just 200. So similar to the one at the top here. So we know that, for example, so I'm going to call it ZR1. If this is the R1, as you want to call it ZR1, so it's going to be Z for the R1 is going to be 200. And assume it's going to be the Z for the R2 is going to be just 100, because the ZR is just the R. And then I am going to go to the inductor. So then I know that the Z for the inductor is just J omega L. That's what we have. So we know that's going to be J times 1000 times 0.1, which is going to be comes out as J 100. So here we have the ZL, which is going to be J 100. So now I have everything as an impedance. So I convert all the capacitance and inductance and resistance to impedance. All of them are in impedance. Now that I have all of them in impedance, the next thing I'm going to do is simply find the equivalent ones like they are all behave as a resistance. So if they behave as a resistance, the next thing I'm going to have is I'm drawing here. So these two are in series. So I'm going to have I have the capacitance up here, that negative J80. Then I have this resistance here. which is going to be 200. And then I have these two are in series. So I'm going to simply just add them together. So I have, assume I have equivalent elements of these two, because one of them is resistor, one of them is the inductor. So the Z equivalent between R2 and L is just add these two together. So it's going to be 100 plus J100. Simply add them together. Now these two are in parallel. So I have these two in parallel. So I can go ahead and say, okay, I will go ahead and put them in parallel. So again, I have these J80, negative J80, negative J80. And then again, equivalent of these two in parallel. So these two in parallel, again, I assume that we treat them as they are both are, I would say, what was it, is both are resistance. So the Z equivalent between R1, R2, and L is, because they're, so it's going to be 1 over, so for is 1 over 200 plus 1 over, let me write it this way. So it's going to be 1 over 200 plus 1 over 100 plus J 100. So if you do this calculation, what you are going to get is going to be comes out as 80 plus J40. And look at these two, and I'm going to write it down on the left. So if I come here, let me draw a line here so I know. Don't mix these two. So now look at these two. These two are in series. So I have this element and this element in series. So the equivalent one is just to add them together. So if I come here and the Z equivalent for all of them is eventually is add these two. So it's going to be negative J80 plus 80 plus J40, which is just if you do the calculation, it's going to be 80 minus J40. So this is how we do that. So if we have some elements together in the AC circuit and want to find the equivalent impedance, is like that. Convert the capacitance, the resistance, and inductance to impedance, the impedance value. When you have the impedance value, simply assume they are all resistance and use whatever method we use it for the resistance to find the equivalent value of that, the equivalent impedance for that entire circuit, the way as we did it here.